Welcome to Subatomic Tanvi.
Hi, everyone.
So, Tanvi, we've all heard of the periodic table of elements, but I've always wondered what's behind each of those little squares in the periodic table.
That's a really good question. So, the periodic table organizes the elements based on their properties, but it doesn't tell the whole story. Think of it like this: each element in the periodic table is like a fully built Lego model, and the standard model reveals each individual Lego piece that make up the Lego models.
That's interesting. So, if I pick an element from the periodic table, then you are saying it's a fully built Lego model,
That's correct.
and the standard model reveals each piece of the Lego that was used to build that model.
You got it.
Wow. I never knew the universe was made of cosmic Lego blocks.
Well, atoms are complex. They're like a million tiny Lego pieces whizzing around. So, let me bring up a presentation on the standard model of elementary particles. And while I do that, a quick note for you all listening to this podcast episode. If you're only listening to the audio of the episode, do remember to also watch the actual video on YouTube or Spotify so that you can see the presentation that I'm about to show you.
Oh, I recognize what you're showing. It's the periodic table of elements.
That's correct. So let's say that we just take a hydrogen atom from the periodic table, and then we zoom into that atom, and what we get is the standard model of elementary particles. So the standard model of elementary particles has two categories: fermions, which are the three generations of matter, and bosons, which are the force carriers. So here we have the quarks, which we spoke about in an earlier episode, and we have the leptons, and electrons are actually leptons, and that's for the fermions. Then the bosons, we have gluons, photons, Z bosons, and W bosons. And we also have this thing called a Higgs boson, which is actually really interesting. We are going to talk about the Higgs boson in a future episode. So that's the standard model of elementary particles. Now let's zoom in a little bit further into the standard model. So first, let's talk about the charge. So here it says 2/3, 2/3, negative 1/3, negative 1/3. So that's the charge of these quarks, and the leptons and bosons have the charges too. So as we spoke about in a previous episode, protons are made up of two up quarks and one down quark. Neutrons are made up of two down quarks and one up quark. So, since an up quark has a 2/3 charge, a positive 2/3 charge, 2/3 plus 2/3 is 4/3 charge for two up quarks. And then for the down quark in a proton, it's negative 1/3 charge. So 4/3 minus 1/3 is 3/3 or 1. That's why protons have a positive charge. And now let's move on to the neutrons. So two down quarks and one up quark. So the one up quark is 2/3, then 2/3 minus 1/3 minus 1/3 for the two down quarks, which would equal 0, which is why neutrons have a neutral charge. So that's how the quarks give the subatomic particles like protons and neutrons their charge. So now let's talk about the spin. So fermions have a half integer spin, as it says here, half, half. And bosons have a one integer spin or an integer spin over here, as it says 1, 1, 1, 1 in the bosons category. Higgs boson has a zero integer spin, which is really interesting. And as I said before, we're gonna dig deeper into the Higgs boson and its spin in a future episode. So now the mass. So the mass is a little more complicated. So over here it says MeV, which stands for mega electron volt. So The mega electron volt signifies energy, not mass, it signifies energy. 1 mega electron volt is equivalent to the energy gained by an electron when its potential increases by 1 million volts. So that's the mega electron volt, but over here it says GeV, which stands for giga electron volt. So a giga electron volt also signifies energy and not mass. So 1 GeV is equivalent to the energy gained by an electron when its potential increases by 1 billion volts, not 1 million, 1 billion volts. And since Einstein already proved E is equal to mc squared, correct, when we know the energy, we can derive the mass from Einstein's equation of mass-energy equivalence, or E is equal to mc squared. So we can rewrite his equation as m is equal to E divided by c squared, and c squared is the square of speed of light. And since the E in this equation represents energy and a mega electron volt or a giga electron volt also signifies energy, we could substitute the value of the energy and make it m is equal to mega electron volt by c squared, or giga electron volt by c squared, which would mean we just found the mass. But over here, I don't know if you noticed this earlier, but it actually says by c squared, or by square of speed of light. So the unit, just MeV or GeV without the by c squared would signify energy, but if you divide it by the square of speed of light, it gives you the mass of the particle. So that's how you find the mass of a particle, deriving it from the energy using mega electron volts and giga electron volts. So this is the standard model of elementary particles.
This is awesome. Well, the next time I look at the periodic table, I'm going to imagine a bunch of subatomic particles having a dance party. Thank you for another awesome episode, Subatomic Tanvi.
You're welcome. Bye, everyone.